Our lesson for today will be looking at Chemistry 1501. The topic for today is ideal gases. We'll be looking at practice questions. Let us start. Before you watch this lesson video, I advise you to watch lesson video based on ideal gases lesson 104, where we looked at equations, an introduction on how to solve these questions. We looked at the equation for calculating total pressure, partial pressure, mole fraction, and also looked at the ideal gas law equation, looked at the number of moles equation. So you will need all the equations and the notes in order to answer these questions that we have here. So the first question, pause the video, work out the question, play the video to verify the answer. The first question says a mixture of 4.5% hydrogen, 76% of oxygen, and 19.5% of nitrogen has a total pressure of 2.3 atm. What is the partial pressure of each of the gases? You should understand that the partial pressure is given in percentage in this case. So in order to get the partial pressure of each, we need to use this equation here. And we have to understand that this percentage is actually the number of moles, or we can say is the mole fraction of each gas here. So we are going to use this equation, x component, that we have talked about in the previous lesson video, equals to P component all over P total. So the x component is the mole fraction, and then P component is the partial pressure of that particular gas that we're looking for, and then P total is the total. So given the total pressure is 2.3 atm. So let us go ahead and find the partial pressure of hydrogen. Remember that the question, it says what is the partial pressure of each gases. So let us start with hydrogen. So for hydrogen we have 4.5%, and then we said that we are going to use this equation, x component, or let us say xx, it's equals to px over p total. So in this case you're looking for this px. So rearranging the equation, you're going to have px is equals to xx pt. Now our mole fraction is given as percentage. In order to convert it to moles, we just divide by 100. So we have 0.045 mole. Remember that if you want to convert this to percentage, we multiply by 100, it will give us 4.5. So in this case, we have px is equals to 0.045, and then our total pressure in this case is 2.3. Then px it's equals to, but instead of px we can just use pH2 because we're looking for hydrogen here. Partial pressure of hydrogen in this case, it will give us 0.10 atm. So this is the first part of our answer. We are done with the first gas. Let us go to the second one. Now we are looking for oxygen. We have 76%. And then dividing this by 100, we are going to get 0.76. Then using our equation for partial pressure, we have PO2, it's equals to XO2 multiplied by P total. So here we have 0.76 multiplied by 2.3. Then we get that Our partial pressure for oxygen in this container is 1.75. So this is the second part of our answer. Let us go ahead and find the last one. The last one is for nitrogen. Then we have 19.5% of nitrogen. Dividing it by 100, we are going to get 0.195 more. Go ahead and use our equation. So we have Pn2 equals to 0.195 multiplied by 2.3. Then Pn2 is equals to 0.45 atm. So this is the second part of our answer. The third part of our answer. In order to verify if your partial pressures are correct, remember Dalton's law. P total should be equals to P1 plus P2 plus P3. Since we have 3 gases here, our equation will end up at P3. So P total should be equals to P hydrogen, partial pressure of hydrogen, plus partial pressure of oxygen, plus partial pressure of nitrogen. So we have found that the total pressure in this case we are given as 2.3. So now we are trying to prove that when we add the partial pressures we are going to get 2.3. So 0.10 plus 1.75 plus 0.45. You'll see that this is indeed equals to 2.30 atm. It's equals to the total pressure. So the correct answers are the ones that we've calculated. It's 0.45 for nitrogen, 1.75 for oxygen, and 0.10 for hydrogen. I hope you got this one correct. Our next question, which is question 2, it says a 2.5 liter sample of 273 Kelvin contains 0.006 mole of hydrogen, 0.0024 mole of oxygen, and 0.0002 mole of methane. What is the partial pressure of O2? So in this case, we can see that we are given different data. So the only equation that we can use according to the given data is the ideal gas law. We assume that all the gases, they obey ideal gas law. So since it's like that, then we can find the partial pressure of oxygen using this equation. Simply substitute our volume, it's in liters, put 2.5. The number of moles we are going to put for our desired gas, which is oxygen. And then our R, we are going to use 0.08206. Then our temperature is 273. Divide both sides by 2.5. Our partial pressure for oxygen will be equals to 0.022 atm. So you can see this is another way to find the partial pressure when you're given information, enough information to use this equation. Our next question. Remember, you pause the video, you work out the question, you play the video to verify the answer. Question number 3 says a 1.5 liter sample of 298 Kelvin contains 0.030 mole of nitrogen and 0.0020 mole of oxygen. If the total pressure of the system is 0.52 atm. What is the partial pressure of the two gases? We have two methods to calculate this. We can use the method that we've used before on the previous question. Just use the ideal gas law. Let us start with our nitrogen. It's P N2 V. It's equals to N of N2 RT. So Pn2 is equals to N2 RT over V. We go ahead and substitute. The number of moles of nitrogen is 0.030. Then our R, it will be 0.08206. Our temperature is 298. All over, our volume is given as 1.5. So the partial pressure for N2, in this case, we're going to get 0.49 atm. So this is the first partial pressure. Then let us go ahead and use the very same method to find the second partial pressure. I mean the partial pressure of the second gas, which is oxygen. So PO2 V is equals to NO2 RT. Divide both sides. We are going to get PO2 is equals to NO2 RT all over V. PO2 is equals to the number of moles of oxygen. We have a 0. Let me verify quickly. It's given as 0.0020. 0.0020 mole. Our R is 0.08206, and then our T it's still 298 all over the volume. It's 1.5. So PO2 is equals to 0.03 atm. Let us go ahead and use another method to actually find the partial pressures. Since from the given data we have the total pressure, which is P total, and then we know that this equation is equals to P1 partial pressure of let us be specific, of N2, partial pressure of N2 plus partial pressure of O2. So we are given this, and then we don't have this, but we know that we have this particular equation. X component, or XX, is equals to the number of moles of X over the total number of moles. By the way, this is a mole fraction. So for X N2, it's equals to the number of moles of nitrogen is 0.030 divided by the total. It will be 0.030 plus 0.0020. That is the total number of moles, the total number of oxygen and nitrogen and oxygen. So we get that the mole fraction of nitrogen, it's equals to 0.94. Reason why we used this equation, because we know that the mole fraction of a particular gas, it's equals to partial pressure of that particular gas over total pressure. So we have this, and then after calculating this, we can basically find the partial pressure of any gas if we have this data. So from here we can say Px is equals to XX P total. So we are busy with nitrogen equals to the partial pressure of nitrogen is 0.94. Then the total pressure that we're given as 0.52. So we get that partial pressure of N2 is 0.49 atm. So you can see it's the same as the one that we got using the first method. Then we can do the very same thing with oxygen. There are many ways actually to use this. We can use this equation, Pn2 plus PO2. Since we have this and we calculated this, we can find the pressure for oxygen. So we have 0.52 equals to the partial pressure. We have found that it's 0.49 plus partial pressure of oxygen. Make PO2 the subject of the formula. So 0.52 minus 0.49 will actually give you 0.03 atm. We can quickly use another method again. This one, it was not covered in the previous lesson video, but you should know that when you talk about mole fractions, the mole fraction of the first gas plus mole fraction of the second gas plus mole fraction of the third gas and so forth, it's equals to 1.00. It's a new equation that you must write it down. So if we have the mole fraction of O2 and the mole fraction of O2, it will give you the sum of 1.00. So in this case, we have found that the mole fraction of nitrogen is 0.94 plus we are looking for the mole fraction of oxygen. It will give us 1.00. We know that the sum is 1.00. Then transpose this to the other side. The mole fraction of O2, we're going to get it as 0.06. Then from here we can use this equation. PO2 is equals to the mole fraction of O2 multiplied by the total pressure. So 0.06 multiplied by 0.52, you'll get that it should be 0.03. It is indeed equals to 0.03 atm. So this is another method you can actually use to find the partial pressure of oxygen. Or from here, actually no, we can start afresh calculating the partial pressure, the mole fraction of oxygen, using this number of moles of oxygen over the total number of moles. Then you know the number of moles of oxygen divided by the total number of moles, and then you get your mole fraction. Then it's either you can use this method or the one I just showed you once you have the mole fraction of one gas. I hope you got it correct. The answers is 0.49 and 0.03. Let us go to the next question. Question number 4. A 500.0 milliliter sample of gases is at 307 Kelvin and contains N2 at a pressure of 1.4 atm and O2 at a pressure of 0.24 atm. What is the mole fraction of each of the two gases? So we are actually looking for the mole fraction. We check what we are given. We are given the volume. It's in milliliters, but we must convert to liters. To convert from milliliters to liters, we divide by 1000, or we multiply by 10 to the power negative 3. So we are given the volume, we are given the temperature. So since we are given the two, you can safely conclude that our ideal gas law can be used and contains N2 of pressure of and oxygen at the pressure of 0.25. These are partial pressures. So we are looking for mole fraction. We can quickly use this equation. Mole fraction, it's equals to partial pressure of that particular gas over P total. This is the first method that we can use, but there is another method that we can actually use. So let us start with our nitrogen. X of N2, mole fraction of N2, it's equals to our partial pressure of N2, we are given as 1.4 divided by the total pressure. Let us quickly calculate it. P total, it's equals to Pn2 plus PO2. So we are given N2 as 1.4 plus 0.25. This will give us 1.64 atm. So this is our total pressure. So we have the partial pressure of nitrogen as 1.4 divided by 1.64, and then we get that our mole fraction is 0.85. Now remember, I said the mole fraction from the first question we were given as percent, and then we started by converting it to decimals, so we can go ahead and convert this to percent by multiplying by 100. Then we are going to get 85% of nitrogen we have in this mixture. Do the same thing with our oxygen, equals to the partial pressure of oxygen over the total pressure. Then we have 0.24 divided by 1.64. We get our mole fraction as 0.15. Multiplying this by 100, we are going to get 15%. So you can see that 85 plus 15%, you are going to get 100%. Let us go ahead and look at another method to solve this. We use this equation: number of moles of that substance over the total number of moles. So in order to find the mole fraction, we need to calculate the number of moles of each substance. Let us start with oxygen. It will be PO2 V, it's equals to NO2 RT. We are looking for this. Our pressure for oxygen we are given as 0.24, and then our volume, like I said, we need to convert, so it will be 0.5000 when we divide by 1000 equals to, we're looking for this NO2 R at 0.08206. And then our temperature we are given as 307. We divide both sides by 0.08206 and 307. We are going to get our number of moles of O2 as 0.0048 mole. So after finding this, we can go ahead and substitute it here. But in order to actually get the mole fraction of oxygen, we need to find the total number of moles. But So far we only have the number of moles of oxygen. So let us go ahead and calculate the number of moles of nitrogen. So we have Pn2 V is equals to N2 RT. Partial pressure of this is 1.4. Then the volume is still 0.5000. N and 2 R it's 0.08206. Then our temperature is 307. Divide both sides by this, you're going to get our N and 2 as 0.028 more. So since we have this, we can find the total number of moles. We have both number of moles, so it will be 0.028 plus 0.0048, which will give us 0.0328 more. This is the total number of moles. Then we can go ahead and calculate our mole fractions. So we have X and 2, it's equals to number of moles of N2 over total number of moles. So the mole fraction of N2 we have 0.028 over 0.0328. We get 0.85. Multiply it by 100, we are going to get 85%. So you can see that the answer that we got using the other method is the same as this one. So for XO2, we are going to get the number of moles of O2 divided by the number of moles total. From here we got 0.0048 divided by 0.0328. Then we get 0.15. Multiplied by 100, we get 15%. So you can see that it's very simple once you get to understand what you're given, what to use, and the methods that you can use to actually calculate what is required. This is the end of the first part of practice questions of this concepts, or let me say chapters. There is the next lesson video of practice question whereby you continue from 5 up to 8. So just make sure that you watch the next lesson video so that you can practice more and more so that you can master this chapter. That's it for this lesson video. This is Wahula SJ. Thank you very much.